And today what we're going to do is continue talking about discrete time systems. Previously, we were looking at how we classify systems, and we looked at one method for doing the job of system analysis, where system analysis, again, is you give me some description of a discrete time system, in this case, a linear time invariant system, some kind of mathematical description. That'll start out being a difference equation. It could be a unit sample response. And as we go further, we'll develop a few other ways of describing system behavior mathematically. But take that mathematical description and apply to it an input signal described either at sample values or another mathematical expression, and perhaps a set of initial conditions on the system. And we need to put those pieces of information together, the description of the input, description of the system, the initial conditions, and come up with a description of the output signal. Now, so far, the only way we have to do that has been through a time domain method, and that was with a recursion table, which lets us take sample values of the input, apply them to the difference equation, and come up with sample values of the output. Today, we're going to work on our first analytical technique that lets us take a analytical expression, a function of n, to describe the input signal x sub n, take that with our difference equation and some initial conditions, and come up with another analytical expression, a function of n, to describe the output of the system y of n. The way we're going to do that today is by actually solving the difference equation for that particular input, that particular set of initial conditions, to come up with a description of the output. That's our second method for time domain system analysis, and the first analytical method we have. We'll also be working on our final version of time domain methods, and that's convolution using the unit sample response that we were developing last time. But today we're going to focus here on how do we solve linear constant coefficient difference equations that describe linear time invariant systems, and combine that with an input signal and determine what the output of the system is going to be. When we discussed the different properties of systems, we said there was something interesting and peculiar about linear time invariant systems, namely that the difference equations that described them were a particular kind. They were linear because it was linear systems, but they were also constant coefficient difference equations, meaning if we put them in our standard form with all the y terms on one side, all the x terms on the other, all the leading values in front of each of the y terms and the x terms could be nothing more than a numeric constant. Couldn't be a function of x or y, that would be nonlinear. Couldn't be a function of n, or that would not be shift invariant or time invariant. And so these can only be numeric constants. That difference equation is our system description. It's what relates the output of the system, y of n, to the input of the system, x of n, and perhaps some previous outputs through the difference equation. And it does so by describing the internal dynamics of the system in the difference equation. And if you think about it, the only thing that's changeable in this difference equation are the actual coefficients, the AKs and the BKs. So really all that determines whether a system is a low-pass system or a band-pass system, or what its frequency response is, where poles and zeros are, all the things that affect the dynamic behavior of the system is just embedded in those coefficients. Just by changing those numeric values, we can drastically change the response of the system. And so if we know the AKs and the BKs, we have described fully our system and its behavior. If we have a linear time invariant system, we can solve that linear constant coefficient difference equation for the output. We can solve it for y of n. Usually we'll solve it for the case where we're applying a new signal, x sub n, starting at index n equals 0. So n equals 0 we define as the time that we introduce a new input to it. That input is x sub n, and we're going to determine what is y of n, what is the output in response to that signal from that same moment on. Now, that may not be the only thing happening in the system. The system may have been responding to some previous inputs, and so that will give rise to some initial conditions, which we describe using values of the output prior to the time that we put in the new signal, y of -1, y of -2, and so on. Those existing initial conditions are the result of previous inputs, things that came in before index n equals 0, stimulated the system, created a response, and the system is finishing off some response to that. Now, we saw last time there's a whole class of systems called IIR, Infinite Impulse Response Systems, who, if you hit them with a unit sample sequence, and therefore with any sequence, their output never quite goes back to zero. So it's pretty common for our systems to still be working on previous inputs when a new one comes along. There's some continuing response happening to those old inputs. That's what's captured in those initial conditions. That's what tells us where was the system and what was it doing prior to when we applied this new input. If I have an nth order difference equation, and remember we get the order of the difference equation from the y side, we find the highest degree of delay in the y side, and that is the filter order capital N. So for example, if I had a difference equation where the highest y delay term is y of n minus 2, that would be a second order system. Now, it turns out in order to solve this difference equation, we need enough initial conditions for each order of the difference equation. So first order system needs one initial condition, and that initial condition is y of minus 1. If I have a second order system, so I have a y of n minus 2 term in it, then I need two initial conditions, y of n minus 1 and y of n minus 2. If I have a third order system that has a y of n minus 3 term in the difference equation, then I need three initial conditions. Notice that all the initial conditions start at y of minus 1, one sample before we hit it with a new input, and keeps progressing backwards from there for however many we need for the number, for the order of the difference equation that we're trying to solve. Now, if by chance all of your initial conditions, y of minus 1, y of minus 2, y of minus 3, all of them that are relevant to your difference equation are 0, then we say that system is relaxed, meaning any response that comes out of the system is solely and completely due to the fact that I hit it with a new input. Nothing's left over. It's all finished up with anything that happened prior to that. That's a relaxed system. Now, the method we're going to do for system analysis for solving these linear difference equation is known as the method of undetermined coefficients, and it exactly mirrors the way we solve linear constant coefficient differential equations. The terminology is the same, the methodology is similar, but the underlying principles are all the same. We're going to be finding the total response of the system, and the total response, we usually determine that by breaking it up into two components. Now, in the traditional way, though, we would break up the total response into the natural response of the system, we'll call that y sub n of n, and the forced response of the system, we'll use yf for the forced response. And if I add those two pieces together, I get the total response. Now, what are these? The natural response, the form of the natural response is determined by the system's internal design, its unique dynamic characteristics, and turns out to be, therefore, what is embedded in the left-hand side coefficients of the difference equation. All those AK terms, the coefficients go with the Y terms of the difference equation. They are what determine the natural response, at least the shape of the natural response of the system. In a discrete time linear time invariant system, all of the natural responses have the same basic form. They're an exponential response function. Now, in continuous time, it was literally an exponential, e to the something. Not so in discrete time. In discrete time, we have some value r that we're raising to the nth power. So we're exponentiating some value. That could be 1/2, that could be 2. We're raising something to the nth power. That's what we mean by an exponential in the context of a discrete time system. And they all have the same basic form of a constant times some kind of something raised to the n power. There may be multiple ones of these r's, and those r's could be real, imaginary, or complex values that we're raising to the nth power. And depending on whether they're real or complex or purely imaginary, we're going to get a different form of the natural response of the system. And so the kind of response we get depends on the form of those. Where do we get those values? Well, again, there may be multiple of them, so we'll use a subscript sub k. They're determined by the roots of the characteristic equation of the system. It comes from the difference equation. What is the characteristic equation? Well, it's the left-hand side of the difference equation, the y terms with all the AK coefficients in the standard form of a difference equation. And we transform that left-hand side, the y side, using a time delay operator, where anytime we have a delay term on the y side, we replace it with a z operator, just like we had the delay blocks in our block diagrams, where z to the -1 meant delay by 1, z to the -4 meant delay by 4 sample values. Well, likewise, if we have a y of n minus k term in the difference equation, that'll be a z to the -k. So we take that y side of the difference equation, use this z operator to replace the delay operations on the y side. So y of n minus 1 becomes z to the -1 operating on y. Y to the n minus 2 becomes z to the -2 operating on y. The coefficients come down. And we find the homogeneous solution to this. We're going to solve this for z, finding the roots of the characteristic equation. So we're finding the homogeneous solution. We're setting it equal to 0. And now we're going to do something that seems strange. We'll treat these operators as if they were sort of algebraic operations. And so that I have y of n in all of these terms that can be actually factored out, leaving behind what we define as the characteristic equation of the system, the polynomial in z that comes from applying the z operator to this difference equation. Now, we're kind of doing a hand-waving description of this as being using a z operator, a delay operator. In a short while, we'll recognize that what we're actually doing is taking the z transform of our difference equation and describing it that way. So that's literally where this is coming from. This particular equation, if we set it equal to 0, has two possibilities. Y of n equals 0. Well, that's not a solution we're interested in. We want something, we expect some response to the system. So that means this other polynomial must be equal to 0. And that's what we solve to find the roots of this characteristic equation. Typically, if we have negative powers of z, we'll multiply both sides by z to the opposite power, z to the +2. So we get a positive exponent polynomial in z, in this case, z squared plus a1z plus a2 equals 0. Factor that, get the roots of that equation, and those roots are what are going to become terms in the natural response of the system. Now, each of those terms in natural response, we know what these roots are. We know they're raised to the n power. We don't know what these k's are. Those are unknown coefficients. Those are the undetermined coefficients we're going to have to find in order to solve this difference equation. How we do that is, well, we have to solve it for meet the requirements of the particular input we have and the particular set of initial conditions that we have. Now, the total response has another component, the forced response. The forced response, its functional form is determined by and actually similar to the forcing function, the input signal that we're applying to our system, generally because we're applying signals that have this particular characteristic. All of our favorites fall in that form. Constants, cosines, exponentials, n times exponentials, n times cosines, all have this characteristic that if I put that shape of a discrete time signal in, the system will respond in its force response with a similar shaped signal. Maybe it's scaled differently, maybe it's got a phase shift to it, but it's basically the same functional form. So that's how we determine what the shape of the forced response is. How do we find the actual values of any unknown coefficients in the force response is by substituting it back into the difference equation itself and determining the coefficients without the initial conditions, just with the forcing function that we're using. Once we determine all those coefficients, well, first we generally find the forced response, then we solve for the unknown coefficients in the natural response and get the total response. So we take that form of the natural response that we determined from the roots of the characteristic equation, along with its unknown coefficients, add in the previously found forced response, including the coefficients that we determined by plugging it into the difference equation, and then solve for the unknown coefficients using the initial conditions. That way we've accounted for what the system's doing due to initial conditions and due to the forced input signal. Now, the standard way to approach these problems, and it may be the way that you approach them in EE328 and or 212. It's also the first method shown in many textbooks, but we're going to apply a slightly different version. And some of you may have learned this similar technique for solving differential equations in 228. It's similar in concept, but the way we break up the problem is different. We still break it up into two pieces, but these are two different components. The zero state response and the zero input response. If I add the zero input response to the zero state response, I get the total response. And I get the same answer that I would have gotten when I added the natural response to the forced response. So it's just another way of parsing the problem to get to the same answer. And even some of the components of what we talked about in the previous approach are going to show up again, just kind of reorganized. The zero state response conceptually is the response of the system isolated to just the part that is due to the fact that I'm stimulating it with a new input. So if the system was still responding to previous inputs, if there were still some initial conditions going on that were driving a response, we're parsing that part out. We're just isolating if the system had been relaxed, if it was in a zero state, here's what it would have done in response to our input signal. So it assumes a relaxed system, and it uses the initial conditions of a relaxed system, namely a zero state, all initial conditions equal zero, in order to solve the unknown things in the zero state response. But again, conceptually, it's just all of the output response that comes from my new input, which leaves the zero input response to be the response of the system to the previous inputs, to the initial conditions, as if there was no new signal, no new forcing function coming along. So we solve the difference equation for the case of no input and just find the part that was due to the initial conditions driving the system, the response that it has to finish out before. So instead of separating into forced and natural responses, the different shaped responses of the system, reorganize it to what was the source of the response. Did it come from the input or did it come from the initial conditions? The zero state response sounds conceptually like the forced response. It's the response to an input signal, but it's not. It includes more than just the forced response. The forced response is in there, but the zero state response also includes a piece of what we were calling before the natural response. Because anytime I hit a system with a new input, when I stimulate it with any input, it's going to give me a piece of response that has the shape of the forcing function, but it's also its inherent design and inherent dynamics will always kick off something that has the shape of its natural response. So anytime I stimulate it, I'm going to get something that looks like the shape of a natural response out of it. So the zero state response, which is the response due to my new input, has that forced response piece, but also has the part of the natural response that was due to the fact that I kicked it with a new input. So we'll call that y of n, but yn2, a piece of it. That leaves behind the part of the natural response that the system is finishing off doing from a previous input or driven by the initial conditions. So it's not the same as the natural response. It has the same shape as the natural response, but it's just a piece of it. So we know the functional form of the zero input response will match the functional form, the shape of the natural response, but it'll have different coefficients than the natural response. So again, what we've effectively done is taken the natural response and split it in two pieces. One part that goes with the zero input response, the part that was due to finishing off old stuff, and the part that goes with the zero state response, the part of the natural response that was stimulated, that was initiated by my new input. Now, if we actually do start off with a truly relaxed system, meaning when I hit it with a new input, it didn't have any leftover response to finish up with. It was truly relaxed. In that case, there can be no zero input response. The zero input response will be zero. Now let's draw some pictures here. Let's say we have a system that we're not stimulating it until we get to index n equals 0, but it had some previous inputs, so its output is still changing, still kind of dying out. This particular one wants to do a decaying oscillation kind of natural response. And here, just a little bit before it was finished with the signal dying out here, we hit it with a new input, maybe a step. And then we measure what the system does in response. And so we get that. And what we measure is the total response of the system. Now, we can break up that total response into various pieces. There's the part of the response where my steady state value changed from down here to up here. So part of the response has the same shape as the forcing function. That's the forced response piece. Now, it may not be the same size step. It could be smaller, could be bigger, but it has the same basic shape. So that jump up in the value was the forced response of the system to my new input. Because I hit it with a new input, it also kicked off a natural response, a big one, that now is continuing on after we show at the end here. That's part of the natural response that was due to the new input signal. Now, if we had done no input at all, the output wasn't finished settling out, and so it would have had a natural response shaped piece that was still working itself out that we show in cyan there. And so the natural response, the total natural response of the system after I stimulate it has two pieces, the part from the new input, the part from old inputs. If we talk about forced to natural response, the forced response is only this one piece, only the step discontinuity that we have due to the step input. And the rest of the system response is the natural response. They all have the same shape. We combine these two together and get the overall natural response of the system. In our new way of looking at this, we would combine the forced response of the system in magenta with the natural response that we kicked off with the new input, the yellow signal, and call that the zero state response. Leaving behind the light blue cyan colored response, the natural response that was due to just the initial conditions or the previous inputs, and that is what we're calling the zero input response. So we're just breaking up the system differently. We're just categorizing this middle piece, the part of the natural response that I kicked off with my new input. I'm grouping that with my forced response instead of grouping it with the initial conditions natural response piece. So hopefully that clarifies how we parse these things differently for this approach. Now, what is the approach? Well, if I have an nth order linear constant coefficient difference equation, it has the form, we have all the y terms on one side, all the x terms on the other, and we're going to begin by solving not the whole difference equation, but a simplified version, a version we call the single input case. The single input case difference equation keeps the left side the same. We keep all of our y terms. But no matter what was on the right side, whatever x terms we had, maybe we had x sub n minus 1s, x sub n minus 2s, so on, we throw away everything except a single input, x sub n. So we've made a simplified version of the difference equation. That's going to give us a straightforward way to find the zero state response for this particular case in a form that it's easy to generalize into the zero state response for the original difference equation, the one we'll call the general case equation. Now, we've preserved the left-hand side, so both the single input case and the general case equation have the same left-hand side, therefore they have the same characteristic equation. Again, as we showed previously, we're going to rewrite the y side of the difference equation using our z operator to give us the delays. and we end up with a polynomial in the new variable z, whose coefficients are the same as the AK coefficients in the difference equation. We're going to take that, which we call the characteristic equation, set it equal to 0, and find the roots of that characteristic equation. So our solution steps are, first we find the 0 input response by developing that characteristic equation and solving it for the case where there is no input. So we set the x side of the difference equation equal to 0. We use the given initial conditions to find the unknown coefficients in the 0 input response. And that gives us the response of the system, the natural response piece that comes from the initial conditions. Then we work with that simplified single input case difference equation and first find the forced response of the system to that, then find the total 0 state response to the simplified single input case by adding the known forced response to a known form of the natural response with unknown coefficients, and then using the particular initial conditions that are appropriate for a 0 state response, namely system is relaxed, all initial conditions are 0, and use that to find the unknown coefficients in our natural response piece here. So we get the 0 state response, the single input case. If our original difference equation was by itself already a single input case, we'd be done. We just add 0 state to 0 input response and get the total response. If we had a more complicated general difference equation that we dummy down to the single input case, then I have to do a step between here and here and take my single input case 0 state response and make it the 0 state response of the general equation, the original equation, which I can do through linearity, through superposition, and time invariance. And we'll see how to do that in an example. And then once we have the general case 0 state response, then we can combine the general case 0 state response with the 0 input response and get the total response of the system. Okay, so what we're going to do is work through an example as we go through these steps, because just describing them in words, they can get very confusing. It can be hard to keep straight which one we're talking about. So let's walk a particular system and solution through the process as we go, as we learn it, and see how the steps unfold. So here's the case we're going to try here. We have a linear time invariant system that has this difference equation. Y of n equals x of n plus x of n minus 1 minus 1/2 y of n minus 1. And I want to know, if that's my system, what's it going to do if I apply an input that's like a big unit step? So x of n equals 2 times u of n. So it's 0 until n equals 0, and then it steps up to a height of 2 and stays there forever. And let's begin with an initial condition. So the system's not at rest, it's not relaxed, and the output at index n equals minus 1 has a value of plus 2. And so we'll use this system with this input and these initial conditions to determine what is the total output of the system going to be for this case. So we have y of minus 1 is plus 2, and then we apply a new input to it, 2u of n, and our job is to figure out what is y of n going to be for n greater than or equal to 0. Okay, let's follow the method. First, we find the 0 input response. And we do that by solving for the case where there is no input. So the right-hand side of the equation equals 0. We're going to use all the terms on the y side, on the left side, and we're going to solve using the given initial conditions. This is the response to those initial conditions. So first we need to find the roots of the characteristic equation and get the form of the natural response from what kind of root we got out of the characteristic equation. So let's go over to a whiteboard to do that. So you should have some spaces in your notes adjacent to the steps where we can actually work this out. And so we're going to start off by finding the 0 input response. And for that, we said we needed the characteristic equation of the system. And that comes from the y side of our difference equation. Now, our difference equation is not written in the standard form here. So let's do that first. Let's rewrite our difference equation. It's y of n, and I'm going to have to bring this minus 1/2 y of n minus 1 to the other side, equals x of n plus x of n minus 1. Now for the zero input part, we're going to be setting the input equal to 0. And for our characteristic equation, then we're going to use this z operator to replace our y of n. There's no delay in that. We have a 1/2, and there's a delay of 1 in our y of n minus 1 term. So we'll make a delay of 1 z to the minus 1, and we'll set that equal to 0. That is our characteristic equation of the system, which equivalently we can multiply everything through by z and have just z plus 1/2 equals 0. And solving for the roots of that, well, that's pretty easy in this case. Z just equals minus 1/2. We only have one root. Notice this is a first order difference equation because the highest delay on the y side is a minus 1. So we only get one root of our characteristic equation, and I only have one initial condition. All right, so we've got our root. Now what do we do with that? Let's go back. We need to find the form of the natural response, the form of the zero input response, which is determined by the roots. For that, we had that table. So we have this table that says, depending on what flavor you get for your root of the characteristic equation, whether it's real and repeated, whether it's complex repeated, maybe even imaginary, we get the associated form of the natural response of the system. We got one real valued root of our characteristic equation, minus 1/2. So that would fall in this category. It's real. It's not repeated. It's distinct. So the root itself that we got creates a natural response that has some form, some unknown coefficient k, times that root, in our case, minus 1/2 to the n. Now we know the form of the zero input response and the natural response. They both have the same basic shape. We just need to find this unknown coefficient, and we use the given initial conditions to determine those. So let's see how that's done. So we're going to use our initial condition. Well, first let's say that our zero input response, which is the same shape as our natural response. We said we'd call this an yn1, a piece of the natural response. We now know it has the form of some unknown coefficient, we'll call it k1, times our root, minus 1/2 to the n. We need to find what is k1. Well, we're going to use our initial condition for that. Our initial condition up here was that y at minus 1 was equal to plus 2. So we plug in minus 1 in for n and get k1 times minus 1/2 to the minus 1 power has to be equal to that initial condition. And a fraction raised to the minus 1 power flips it over. So this is like a minus 2 k1 equals plus 2. So k1 must be minus 1. And our zero input response has to be minus 1 times minus 1/2 to the n. And that's going to be true for n greater than or equal to 0. That's our zero input response. So that's the first piece. We have the zero input response. Again, we used the initial conditions to find it. We used the case of input was 0, and now we have the first part of the puzzle. Let's go back and see how to handle the rest of it. Okay. Now we have to work with that single input case. We need to demote our system to a simpler form. And for that, we're going to take that single input case and find first the forced response. And the form of the force response comes from the form of the forcing function using our table, again, another table that says, depending on what flavor, what shape of input we're applying, we get a similar shape with different coefficients in the forced response. Well, let's take a look at what we have. Let's take a look at our form of our difference equation. We're going to be working on our zero state response. But first we have to start with this single input case. What is the single input case? Well, our difference equation for the single input case is the same as our original difference equation, but on the y side it's the same, on the x side it's not. So we still have our y of n, still have plus 1/2 y of n minus 1. And if we had written out the entire difference equation, it would have been equals x of n plus x of n minus 1. But for the single input case, I'm going to leave off that. So I have just x sub n, no coefficient in front of it, nothing multiplying it, nothing added to it, just x sub n by itself. And that's what makes it the single input case. And we're going to find the zero state response for this version and then use that in a simple way to find case for the general case equation. All right. How do we do that? Well, first we need to find that forced response. We're going to call that little yf of n. And according to our method, it says take a look at our input signal. Well, here's our input to u of n. Right, our input 0, 0, 0, 0, and then steps up to a height of 2. And that chart we look up, and we look over here for the form of that input signal, and I don't see anything that looks like a step function. Well, that's because these are more looking at not what happens right at the starting instant, but what happens afterwards. What is the shape of the signal after we've gone through turning it on? And in the case of our step function, well, anywhere I look in that step function, let's look at it. Once I get it launched off, anywhere along here, it looks to me like a constant. And so we would consider this to be a constant style input. And according to that table, if I have a constant input, our force response is also a constant. Now here, our x sub n was a constant 2. The force response is going to be some unknown constant. We'll call it C1. So how do I determine what C1 is? Well, I'm going to use the single input case difference equation, and I'm going to plug y of f, my assumed version of it, into the single input case difference equation. So that I'm basically going to say, well, this has to be a solution of that equation. If I replace y of n with y forced, it has to be true that y forced plus 1/2 y forced of n minus 1 has to be equal to the actual input x sub n that I know is 2, or 2u of n if you prefer. And y forced, I said, is C1. And what is y forced of n minus 1? Well, again, if I'm downwind a little ways, if I'm at this sample and I look back one sample prior, I have the same value. And so yf of n minus 1 for a constant input is the same constant. And these are going to set that equal to the actual input signal, which has a constant value of 2. And so that's all I need to find my unknown constant C1, as we have it 3/2 of C1 equals 2. So C1 must be 4/3. And we have our first piece, our first forced response piece, going to be a 4/3. And that's going to start at n equals 0. So I can write 4/3 times a step function. And we have part of our answer. Now, let me reinforce, this is the forced response of the single input case equation. the one where we drop things off. It's not the forced response for the total system. We got to come back and figure that out in a minute. But for the single input case, this is how we would get the forced response. That's not the whole deal for the zero state response, however. We still need the rest of it, the natural response piece. And let me use a shorthand instead of this long ZSR SIC thing. Let's call this the zero state response Y ZS, and I'll use a 1 to remind me. This is for the single input case. Has two components, has the forced response piece, and it has another natural response shape piece. I know what this one is. I've already just found it. It's 4/3. The natural response piece, I don't know how big it is, but I know what shape it is. I figured that out when I did the zero input response. And so I can take advantage of that and say, well, this has the form of -1/2 to the n, but I don't know how big it is, so we'll put a unknown coefficient out in front of it and have the single input case zero state response form. Now I need to find this unknown coefficient, and we need an initial condition to do that. So we need the right initial condition for a single input case zero state response. That's not the one we have here. We have a zero state response, so we have to do the initial condition for a zero state. Well, I only have one of them, and that is y of -1 has to be 0, relaxed. So using that, let's plug in n equals -1 to our zero state response equation, set it equal to this value, and solve for k. So we get 4/3 plus k2 times -1/2 to the -1 has to equal 0. So that's 4/3 minus 2k2 equals 0, which leads us to k2 equals 4/6 or 2/3. When we solved the zero input response, that was the response of the system to this initial condition. That's what we found in when we were solving that previous part, the zero input response. Now we're trying to find what is the response of the system to the new input if there was no initial conditions, if the system had been relaxed. So we're trying to isolate the part that was due to my new input. So I'm leaving off this initial condition. That produced my zero input response. I'm solving for the case that as if my system started off relaxed, which is all initial conditions equal 0. Solve for the k back in the zero input response, right? We plugged in this initial condition, y of index -1. We replaced n with -1 and set that whole thing equal to +2. That gave us the natural response piece that was due to this initial condition. So we've already accounted for that. Now I'm trying to account for, well, what's the system going to do with the fact that I hit it with a new input? And in order to create that condition, I have to use a relaxed system. And so I'm imposing that as my initial condition here, using that to solve the zero state response. Okay, so in total then, we have that our zero state response is the sum of these two. So it's the 4/3 plus k2, but now I know my k2 happens to have a value of 2/3. And so we can summarize this by saying our zero state response for the single input case, the simplified version, is 4/3, and that starts at n equals 0, plus 2/3 times -1/2 to the n, and again, times u of n because it starts at n equals 0. That's the zero state response for my simplified version of the difference equation. Now, I want to take this x away. I want to know what's the zero state response for the whole thing. For that, we need to go quickly back to PowerPoint, show you how to do that real quickly. So we went through all these steps, basically, that were outlined here. We found the forced response. We plugged it into the single input case difference equation. then found the zero state response for the single input case using all initial conditions equal to 0, adding the forced response to the natural response with an unknown coefficient, and solve with that 0 initial condition. That gave us the zero state response in the single input case. Now, if we wanted the total single input case response, we would add those two pieces, but that's not what we're after. We want the solution of the original differential equation, or excuse me, difference equation, that general case equation. And here's how we do that. If you've got things on the x side of the equation, you've got a b0 x sub n and a b1 x sub n minus 1, and maybe some more delay terms. If you've got a whole bunch of those, we find that single input case, the case where I just have x sub n on that side, and use linearity and superposition to find the zero state response for the bigger equation, the general equation. If my input is some ax plus b x sub n minus 1, and I found the response that system was our zero state response, I'm going to do everything to the zero state response from the single input case that the equation tells me to do to x sub n to find the zero state response of the general case. And that's just using linearity that says if you put in x1 and get y1, if I scale the input by a, I scale the response by a. If I add a bunch of responses or a bunch of inputs, I add the responses. And so superposition holds, as does time invariance. Any delay on the input creates the same delay on the output. Those are the principles that we're applying here to generalize the single input case zero state response to the general case. So if I have more than x sub n on the right side of the equation, I find the overall zero state response of the general, more complicated equation by taking the single input case zero state response and doing everything that happens to x on the right side of the equation. Multiply it, delay it, anything that it says to do over here, we do to the single input case zero state response. That gives us the general case zero state response. We add that to the zero input response to get the total response. And for our particular case, we found our zero input response was -1 times -1/2 to the n. Our zero state response from the single input case was 4/3 plus 2/3 times -1/2 to the n, all times u of n. That means the general case, which says has x sub n plus x sub n minus 1 in the difference equation, says take this single input case, take it and add another version of it where n is replaced with n minus 1. So we get a 4/3 u of n minus 1, a 2/3 times -1/2 to the n minus 1 power times u of n minus 1. That's the general case, complete zero state response of the general system. Then I add that to our zero input response and get the total response. That's how we do the solution of linear constant coefficients difference equations. We'll pick up with some special cases that we have to deal with in this solution on Wednesday, but that's the first that's all the steps that we need to know other than these special cases for solving any linear constant coefficient difference equation.